because limits are the pretty strong basis for a big part of the or a part of the big ideas in calculus. So let's explore a little bit. Okay, let's look at this first thing. We're going to talk about continuity. Whoop, sorry about that one. We're going to talk about continuity. So let's look at this very first function. The very first function is the line y equals x plus 3. That's just a linear function. You're used to a linear function. And we know that with a linear function, no matter what we do, if we make, let's just say, a table of values, if we make a table of values here, anything we put in for x will give us an output for y. Anything, doesn't matter. If we put a -3 in, the output is 0. If we put in -√2, the output is 3 minus √2, or -2 plus -√2 plus 3. If we put in 0, everything is fine there. So it doesn't matter. This function is continuous. Everything exists. This line has no holes, no gaps, nothing like that. So this is a nice, smooth function. Okay, that's kind of an introduction to continuous. Let's do a little introduction with limits at the same time on something that's kind of nice and mellow, like a linear function like y equals x plus 3. So if I were to, I'm going to call this function, I'm going to give it a name so it's a little bit easier to talk about. Let's call this function f of x. So f of x equals x plus 3 is the function that we're looking at. Sorry about the clicking. If you hear clicking, it's my Apple Pencil on the iPad. You're going to have to get used to that one. Sorry, because I love my Apple Pencil, especially with Notability. Oh my goodness. Oh, you know what I realized? I didn't even talk about the goal. Oh my goodness. What kind of a teacher am I? I'm going to turn this so we can see it a little bit better. Oh, that doesn't work in the recording. Okay, so let's look at the goal. Looking closely at some interesting and not so interesting points on a function. The interesting ones are more interesting, but we'll look at some non-interesting points too. And the reason it reminded me to bring up this goal is because that's what we're going to do right now, is look at some not so interesting points on this linear function x plus 3, because everything exists on this line, so it's not so interesting. There's nothing weird going on, but it's a good way to introduce the notation of a limit and what a limit is actually doing for us. So let's look, for example, at the limit, and the wording of this is going to be really important. The limit of f of x as, let's just say, x approaches 5. Okay, so did you get the wording of that? The limit of f of x as x approaches 5 is how we say it. So what we're saying is, what is the value of the function as x gets closer and closer to a value of 5? So that's what we're looking for. When we're looking at a limit, what we're really saying is, what is the value of f of x? Getting closer to. As x gets close to 5. So in this case, this is one of those not so interesting points because it's pretty clear. There's nothing strange about this. As x gets closer and closer to 5, so here's where x is equal to 5, of course. And so we're saying, what is the function value going to be as x does get closer to 5? So what we have to think about here is And in this case, not so interesting because this is a continuous function, is what is the function doing as we come from the right side as if we come from the left side? It doesn't matter in this case so much because this is continuous, everything's happening the same, but if I come from the right side of 5, in other words, value is bigger than 5. And then if I come from the left side of 5, so value is less than 5, what value are we getting closer to on this function? What is this? Well, in this case, it's pretty easy to see. This is a linear function. The y value is getting closer and closer to 8. Of course, 5 plus 3, that's 8. So this one is not as interesting as some others, but it's a good way to get started. It's a good way to think about the notation, and it's a good way to start thinking about a limit and a function being continuous. So let's go on to something a little bit more interesting. Okay, the next function is this rational function. And when I graphed it on Desmos, interestingly enough, it looks exactly like the last function. It looks like the line x plus 3. But if you remember from pre-calculus, I hope you do, if we were to make a table of values for this, and if I were to plug in values, most of the values are okay. So, I mean, if I think about some of the values I plugged in from the last one, I can't remember, so I'm going to look back. If I plug in -3, -√2, I'm going to get all of the same values I did before. If I plug in -3, I get 0. If I plug in -√2, I get 3 minus √2. If I plug in, what else did I plug in? 0 and 1.5. If I plug in 0, I'll also get 3. If I plug in 1.5, I'll get 4.5. The issue, though, is when I plug in -1. And I'm going to actually show the work here. If I plug -1 in, I end up with, so let's call this function g of x. That's going to make this easier to talk about. So if I look at g of -1, look at this. This is a good pre-calc review and some calculus at the same time. I love it. So if I find g of -1, plugging in -1 squared plus 4 times -1 plus 3 over -1 plus 1. In the numerator, that's 1 minus 4, which is -3, plus 3, that's 0, and then -1 plus 1, also 0. Uh-oh. I don't think we can divide by 0, can we? We cannot divide by 0. That's not allowed. We cannot divide something into groups of 0. And they're not groups after all. So when we plug -1 into this function, even though it doesn't show it in that picture that I have there, we get something that is undefined. This doesn't compute. This doesn't make sense. This point does not exist. This is a really important point here. What that means is that this function is not continuous at x equals -1. That point is undefined. Okay, so we're going to say g of x is not continuous at x equals -1. So what we have to be careful about, and I hope you're writing all of this down. These are the notes that you should be taking. This is a great example of things that would be in your notes so you can go back and look at them later. Because watching this video over again is going to take way more time than just flipping through your notes. Unless you want to hear all of my jokes again, I can't blame you, but to each his own. But really, you should be writing this down. So g of x is not continuous at x equals -1. But if I say, let's find the limit like we did before. So the limit of g of x as x approaches -1. Okay, we're going to look at this the same way we did before. As x approaches -1, I'm going to move my g of x out of the way here. Let's move it up here because that's nowhere near -1. So as x approaches -1, here's -1 right there. What we're looking at is from the left and from the right. Now we know that that point does not exist. We're going to look at it closer in just a minute. This point does not exist. But if I look from the right and I look from the left, it looks like we're still approaching a value. We're getting closer and closer to some value. And according to Desmos, that y value, the function value that we're getting closer to, is 2. And that kind of makes sense. I mean, remember we said this is just like the graph x plus 3. Well, -1 plus 3 is 2. So this limit, the function, is getting closer and closer to a y value of 2. Now this is where the limit part comes in. We'll never actually equal 2 on this function. That is the interesting part. So remember I said looking closely at some interesting points on a function, this point is interesting because we don't ever reach that value, we're approaching it. This is a really, really important concept in calculus. Sometimes, you know, it's not that we are equal to that value, it's that what is the behavior of the function as we get close to that value. So remember the definition is what is the value g of x is getting closer to. Oh, sorry for that clicking of the pencil, but is getting closer to as x approaches -1, and I'm going to add this on now. This is our informal definition of a limit from the right and the left. And it's going to come in, this will be more important later on in different types of functions, but it's something to remember. Oh, look at that weird function below. We'll get there in a second. So g of x is not continuous at x equals -1. We were undefined there. You probably know that this was a hole in the graph. We'll talk more about that in a minute. So we say it's not continuous at -1. However, the limit is something that is defined. We say that the limit does exist because the function is getting closer and closer to a y value of +2 as we approach -1 from the right and from the left. Okay, that's just an introduction so far. Let's see if we can get a little bit deeper now. Let's talk more about this interesting rational function. Let's talk about it a little bit more carefully. You've learned in pre-calc, whether you remember or not is a different thing, but you've learned it. In pre-calculus, you've learned about finding discontinuities or holes in a graph or vertical asymptotes in a graph. And what you learned in pre-calculus was that if you could factor things, it's going to give you a little bit bigger idea about what's happening. So in this case, g of x is x squared plus 4x plus 3. And I'm pretty sure you explored in pre-calculus, if you factor that numerator, and the numerator factors out to be x plus 3 times x plus 1, you saw that this factor right here, those two factors are the same. Those two factors become that big fancy 1, meaning they reduce out to be 1. That's a fancy form of 1, I guess. So what we call this, because those two factors, we call them, it's removable. We were able to reduce it down to 1. We call this a removable discontinuity. We were able to remove that factor from the expression in general. So we say that g of x has removable discontinuity. Discontinuity, it's not continuous there, and we knew it was not continuous at x equals -1 because that's where the hole exists. So g of x has removable discontinuity at x equals -1. In other words, g of x has a hole at x equals -1. But the limit exists. The function is getting closer and closer to a y value of 2. So this isn't one of those interesting points on a function. The point actually does not exist on the function, but we can talk about what is the function doing as we get closer to it. So I graphed this in Desmos. I zoomed way in on that removable discontinuity, and this is what it showed me. Really hard to see. It's actually easier to see on your graphing calculator. And I would recommend that you graph this function in your graphing calculator right now and go zoom in on the point x equals -1. Your graphing calculator shows that hole way better than Desmos shows a hole. Desmos is just freaking out when it gets closer to -1, but your calculator will show it way more clear. So what I'm going to do from now on, because I won't be using Desmos or the calculator to do these, I'll be drawing these by hand, and you will too. I'll be drawing the function to look more like this. So if we have this function g of x equals x squared plus 4x plus 3 over x plus 1. If I were to graph this by hand, this is how I would show it, and this is how you should show it too. We already know that there is a hole in this graph, and by looking at the graph up above, we know that the hole is here when x is -1, and we know that that hole exists because we're getting closer and closer to 2. We know that the hole exists right here at this point, -1, 2. And then we know this kind of resembles the line x plus 3. So here's our g of x function. That's how we show this hole, that removable discontinuity. Okay, well, a lot just happened there. So let's talk about this. Let's just recap everything we've learned. We learned that there is a hole in g of x. Or removable discontinuity. Oh, I'm running into my line. There's a hole or removable discontinuity. I'm going to take those parentheses out and put it as part of this sentence. On g of x at -1, 2. The limit of g of x as x approaches -1 is 2. Those two things are related on purpose. That's one way to find the hole. Where does the hole exist? Where the limit is. What is the limit as x approaches -1? That's where the hole is. That's at 2. We'll spend way more time doing this, finding those holes in a moment. But for now, let's just start to get the idea. Okay, let's move on. So that's removable discontinuity. That's the hole in the graph. We've looked at limits. We looked at some of the notation of limits really quickly, kind of some informal definition, and that's all we'll do is an informal definition of limits. Let's go on to the next type of discontinuity. We have this function here, 5 over x plus 2. There is not a factor of x plus 2 in the numerator. That can be removed. So we call this one, take a guess, think about it, non-removable discontinuity, of course. Let's call this one h of x. I swear I get funnier. That wasn't funny. I get funnier, I promise. You'll get used to it. So we'd say that in this case, there's a discontinuity. If we were to create a table of values, let's say we put in -1, we have 5 over -1 plus 2, that's 5. And you can see that point here on the graph, there's -1, 5. If I plug in 0, I end up with 5/2. But if I plug in -2, that's when things get weird. So if I say h of -2 is 5 over -2 plus 2, 5 over 0 is undefined. The function up above was also undefined at -2. So why can't we just say this one also has a hole in it? Or why is this not removable discontinuity? Well, that's because there is no factor of x plus 2 to remove. That x plus 2 is a factor that stays in the denominator. That factor is not removable. So what that does for this function is that adds this vertical asymptote, which Desmos doesn't show, but if we were to graph by hand, this is how we would denote a vertical asymptote. That is a discontinuity in this function, but it's a little bit more substantial. It's something that's way more visible. It's easy to see that at x equals -2, this function is undefined. So this is what we say here. Now, if we say that h of x has non-removable, well, let's do it this way. I'm going to do it in the same order. Has a vertical asymptote. Or non-removable discontinuity. At x equals -2. Okay, we can see that non-removable. There was not a factor we could remove that would create a hole in the function. Instead, we have a vertical asymptote. That's non-removable discontinuity. Let's talk about the limit. Remember what we talked about before. As x approaches -2 from the right and from the left. So let's see. I'm going to use a different color to make this stand out. The limit of h of x as x approaches -2. That's what we're going to be looking at. So from the right and from the left. So I'm going to show you something. I think you might have seen it. It was kind of a sneak preview. Something that we call one-sided limits, because when we look at a limit, we're looking at it from two sides, from the right, from the left. So if I approach -2 from the right, so if I follow the function from the right side of -2, that's what's happening. If I follow the function from the left side of -2, getting closer to -2, look what the function is doing. This function is doing two different things from the right side and from the left side. And that's what we call one-sided limits if we start looking at those two sides as separate entities. So let's do that. So if I say, let's find the limit of h of x. I'm going to write this bigger because this is going to be new and you need to see this notation. The limit of h of x as x approaches -2 from the right side. That's what that little plus means. From the right side means that I am looking at values that are bigger than -2. Okay, so what we look at is we say, all right, well, what is the y value? What is the function value as we get closer and closer to -2 from the right-hand side? Well, we can see because there's an asymptote, this function is not approaching one single value. The y values are getting bigger and bigger and bigger. We're approaching an asymptote. So from the right side, I would say that this function is approaching infinity, a very large number. Okay, let's keep going. If I look at the limit of h of x as x approaches -2 from the left side, so the left side is values smaller than -2, I can see that the function itself, those values are getting smaller and smaller. We're approaching the asymptote. So these two, or this function is approaching -infinity. Okay, but we haven't actually answered the question I was asking of you. I asked originally, what is the limit of this function as x approaches -2? That means looking at the left and the right at the same time. So let's pull this all together. If I then look at the limit of h of x as x approaches -2, remember this means from the right and the left. We're looking at what is the y value this function is approaching. Well, this function is not approaching one y value. From the right, we're approaching infinity. From the left, we're approaching -infinity. So we say there is not just one y value that this function is approaching. So we would say that this limit does not exist. There is not one y value this function is approaching from the right and the left at the same time. And because we're lazy, we say D&E does not exist. Don't use this whenever you're unsure of an answer. Make sure you are very, very clear about why the limit doesn't exist. So let's be very, very clear. This limit does not exist since the limit from the left and right are not equal. Okay. Wow. That was a lot. You have now looked at some idea of continuity. Informally, we've looked at removable continuity. Well, we looked at a function that is continuous. So I guess I didn't say that before. F of x is continuous. On the domain -infinity to infinity. This function is continuous everywhere. Every point is there. Nothing's really interesting about it. Every point exists. There's not a hole. There's not a gap. There's not a vertical asymptote. Continuous. We looked at g of x. G of x has removable discontinuity because g of x had a hole in the graph. However, the limit still existed because the function was getting closer and closer to 2 from both the right side and the left side. We saw that hole here. Removable discontinuity, the limit does exist. And then we looked at this non-removable discontinuity, this vertical asymptote. And we saw by using or looking at the one-sided limits, we saw that the limit at this non-removable discontinuity does not exist. We're approaching positive infinity from the right, negative infinity from the left. Okay, I hope you're pausing, you're letting this sink in. If you have to go back and listen to that again, do it. Because now we're going to put it to use in a couple different situations. Piecewise functions are probably the best way to look at limits in different situations, because piecewise functions have some really interesting points. So we're going to look at different limits as x approaches 1 and then x approaches 3. We're going to start with those. Then we'll look at some one-sided limits as x approaches 2, and then we'll look at as x approaches 0 because it's an interesting case. So let's look at as x approaches 1. The question is asking, what is the limit of f of x as x approaches 1? Notice there's not a plus sign here, there's not a minus sign. So what this means is we need to look from the right and the left and make sure they're the same. So we're going to look at both from the right and from the left at the same time, make sure those two values are the same value, and if they are, then this limit will exist. That means the function is approaching some y value as x gets closer and closer to 1. So let's go take a look as x approaches 1. Okay, as x approaches 1, we're going to look at x values that are bigger than 1, and if we plug those into the function, I can see that as we get closer and closer to 1, even though they're bigger than 1, as we get closer and closer to when x is 1, we're getting closer and closer to this y value. From the left side, as x values get closer and closer to 1, the y values are getting closer and closer to the same value. So I can see that as x approaches 1, the y value of this function is 3. So f of 1 is approaching 3. That means this limit exists. Even though there's a hole there, the function is still approaching a y value, getting closer and closer to it. So we'd say as x approaches 1, this function is getting closer and closer to a y value of 3. Okay, let's see if we can do the next one. The next one is asking, what is the limit of f of x as x approaches 3 this time? So as x approaches 3, we're going to look from the right. We're going to look from the left. Oh, but wait, what about this? Remember, we're talking about what is the function approaching. That means what are we getting closer and closer to? Don't forget that this is a piecewise function. The piecewise function has all kinds of parts and pieces to it. What a limit is asking is, what are we getting closer and closer to? What are we approaching? We don't approach this point. It just exists in space. The function is not approaching that point from the right and left. Instead, the function is approaching this point from the right and from the left. So this is a cool one. This is really different. But you have to realize we're following the function, getting closer and closer and closer, closer and closer and closer, creeping up on that value when x is 3. So in this case, the y value that this function is getting closer to, so the y value of that hole is 2. So we can say that f of 3 is approaching 2, even though f of 3 is equal to 3. That's what this is. This point 3, 3 is a point on the function, but that's not what we're concerned about. We're concerned about what is this approaching. All right, so that limit is 2. That's what we're getting closer and closer to. We're getting closer and closer to that hole. All right, let's look at some one-sided limits. Remember, this is saying that we are approaching 2 from the left. So that means the smaller values to the left of 2. Let's go take a look at the graph, see what that looks like. So here's when x is equal to 2. And we're looking at as we approach on the function from the left side of 2. So that means we're concerned about this side because these are x values that are smaller than 2. And what it looks like is from the left side, we're approaching a y value that is 3. So f of 2 from the left is approaching a y value of 3. That's what that hole is. That hole has a y value of 3. So we'll say 3 on this one. Okay, the next one is asking, what about from the right? What is the function approaching? What is the y value for values that are to the right of 2 on the x-axis? So let's go take a look at the graph. You might have already been doing this. From the right side of 2, so we're looking at this function right here. As we're getting closer and closer to 2, I can see that we have a y value, or a hole there, y value of 1. So we'd say that f of 2 from the right is approaching 1. The hole is at 1. Oh, shoot, sorry. The hole is at a y value of 1. Okay, so now if we come back to part E. Part E says, find the limit as x approaches 2. There's no plus, there's no minus, so this one's asking from the right and left together. And I can see that from the right we approach a value of 1, from the left we approach a value of 3. This function's not coming together at one spot. Those two limits are different from each other. So we'd say that this limit does not exist. We are not approaching the same value from the right and from the left. Okay. Oh, let's put in a little reasoning. I mean, it's really good for you. We're just taking notes for the first time. So function is approaching different values from the right and left. Okay, last one on this interesting piecewise function with its really interesting points. Notability is froze. Hold on 1 second. Let's try this again. Okay, last one we're going to look at is now as x approaches 0. Notice there's not a plus or a minus there, so we're looking from the right and left. Right and left. So let's go take a look at the graph. As x approaches 0, so here's 0. From the right, I can see we're getting closer and closer to that y value of 3. From the left, though, there is no function. We're not approaching anything from the left. This function doesn't have any values to the left of 0. Therefore, we would say this limit does not exist. We have to be able to approach from the right and from the left. But this function doesn't exist from the left. Therefore, this limit doesn't exist. We are not approaching a value from this left-hand side. So from the left doesn't exist. So we would say that the limit as x approaches 0 also does not exist. And the reason for that is because we can only approach this point from one side. It's an endpoint, so that limit does not exist at that endpoint. Okay, I think I'm going to pause here before I move on because I think that's enough to take in. And I'm going to give you some practice problems where you're just going to be looking at a graph. You're just going to be looking at whether or not a limit exists from the right and from the left based off of a graph that I give you. And then in the next lesson, we'll start looking at how to determine those limits without having to graph a function every time. So we're going to look at some algebraic ways to determine whether a limit exists. You're doing awesome. You're doing great. I'll answer more questions when we come back together. But for now, give this a try.